Hi everyone, my name is Jackie Lin from Bucknell University. One of the outstanding questions in ecology is the species diversity. Inspired by the observation of bacteria coexisting in a community, we explore the emergence of spatial structure given a simple cross-feeding mechanism between two species. By studying these patterns, we investigate the interaction between two species, where one species produces nutrients that are essential for the other, and vice versa. We use an agent-based model for two-dimensional square lattice, where each lattice side is occupied by at most one species. We use kinetic Monte Carlo algorithm to simulate multiple processes, where each process is randomly chosen and carried out. Figure 2 shows some colony examples generated by the model. A colony consisting of circular sectors, spiral patterns, and engulfment patterns. At the beginning of each simulation, we use two initial conditions, as shown in Figure 3. One is a square box with randomly placed species, another is a circular with separated placed species. To better understand and quantify the properties of the colony, we categorize each colony into types from interfaces as defined in Figure 4. Consider the separated initial condition. There are two types in this simple colony, as shown in Figure 5. By simulating and analyzing the movement of types, we summarize all possible morphologies that can occur. Note that only the engulfment and the spiral pattern is stable. Other patterns are likely to transform into two stable patterns. I will introduce some key findings in our simulation. To explain why other patterns are not stable, we universally place nutrients in the lattice, and we observe the radially growing sector-like patterns as shown in Figure 6. This pattern has a lower interface fluctuation than colonies solely relying on cross-feeding. We use a sliding window matrix to quantify fluctuation, showing the importance of nutrients availability in this model. Another finding is the contribution of growth rate to the morphologies of the colony. At low nutrient diffusion rate, we observe the increment of radius and angle scales with the growth rate, as shown in Figure 7, indicating turning the growth rate only applies to the acceleration of pattern formation. Nonetheless, with the high nutrient diffusion and the high growth rate, island-like shapes emerge at the front of the colony as shown in Figure 8. These island-like shapes enhance the roughness of the colony. Here, compared to the colony with different nutrient diffusion, the higher nutrient diffusion results in a more rough boundary. In conclusion, the nutrient availability in the boundary of the colony determines the morphologies of the colony. When nutrients are abundant, the colony expands in radial sectors. When they are limiting, two species grow along an interface, resulting in a spiral pattern. The transformation is explained by the annihilation of two neighboring tips. Thus, directly related to the nutrient distribution, the key parameter to change the colony morphology is nutrient diffusion rate. The future work is to quantify some properties of the colony and explore the contribution of the other parameters to the morphological changes. That's all I have. Thank you for listening.